It's probably not possible to get too much practice drawing free body diagrams. So in this one, we're going to draw 3 more. I'll draw them one at a time so that we can draw them bigger and pay some more attention to the components and to the summing of forces that we'll put into the left-hand side of Newton's second law. Here's the first one. It's an elevator. So here's an elevator with some rope attached to it, and some motor is pulling this thing up so that the elevator has an acceleration in the upward direction. Inside the elevator is a box with some mass. Looks like this, right? We're going to draw the free body diagram for this box and then write out the left-hand side of Newton's second law, which tells us to add up all the forces as a vector and set it equal to ma as a vector. All right, what does the free body diagram for this box look like? Well, it's a box, but it could be a potato or a carrot or a Dotson. So I'm going to draw it as a dot because it doesn't matter. That helps me focus on the forces, not on anything else. It's the forces that matter here. So there's mg, the weight that's going straight down. If the box has mass, it'll have weight. And then the floor is touching the box, so it can exert a force on it. And that's our friend, the normal force. It's going to go straight up. And that's it. Those are the only 2 forces that act on the box. You might wonder about this acceleration. Surely that's giving us a force also. It's important to note that on free body diagrams, you draw forces. You don't put accelerations. What's going to happen here is that when we add all the forces up, it'll equal mass times acceleration. The free body diagram is to help us draw the left-hand side, where the forces are. The acceleration comes on the right-hand side, and we'll do that part separately. So when you're drawing your free body diagram, only put forces, the weight vector, and then a force from things that are touching, pushing and pulling on the object. If you add all of those up, the result of it is ma. So this acceleration is going to be the result of all of the forces that are acting on it. So let's go ahead and add them here. We'll take up to be the y direction. So we're going to add all of the forces in the vertical direction and set it equal to ma in the vertical direction. Okay, go to the free body diagram and add up every force in the vertical. Normal force minus mg. That's the left-hand side that came from the free body diagram. Now on the right-hand side, we have may, which in this case is going to be m times this acceleration. But the important thing here is that the left-hand side comes from the free body diagram. All right, so there's that case. Let's look at 2 more. I'll erase this one. The next one is going to be a box on an inclined plane. Looks like this. So here's a ramp or an inclined plane at some angle theta. There's a box on it. It's got some mass. So there's our object. And this thing is held in place by a string that is tied to a tree. So it's not going to go anywhere. We want to draw the free body diagram for this box and populate the left-hand side of Newton's second law. All right, what does the free body diagram look like for this box? Here it is. I'm going to draw it as a dot because it might be not a box, but an ear of corn. It doesn't matter what it is. Now, I know that there's a weight vector acting on it, and the weight acts straight down, mg. And then I'm going to look for things that are touching the box, pushing or pulling on it, that'll give us a force. And I see 2 things. I see this surface that will exert a normal force on it, and I see this string that'll exert a tension on it. The string is going to be parallel to the ramp, to the incline, and the normal force is going to be perpendicular to the incline. So when I want to draw my free body diagram as neatly and accurately as possible, I need to give myself a reference line here that is aligned up with the ramp. So I'm going to draw this dashed line through the dot that indicates the ramp. So that is the angle theta right there. And then I have the normal force perpendicular to it, and I have a tension force parallel to it. Okay, there are the forces that are acting on this box. Now, I have forces going sideways and up and down and off at angles in this case. So when we add up the forces, this is a little more complicated than our last case. I have to add up the x component of forces, set it equal to max, and I have to add up the y component of the forces and set it equal to may. The first thing to do is to choose a coordinate system. It turns out that it's often convenient when you have a ramp to rotate your coordinate system so that the x-axis goes along the ramp and the y-axis is perpendicular to the ramp. Now, why is that convenient? Because two of the three forces that are showing up on this free body diagram are aligned with that coordinate system. If I rotate my coordinate system so that x is this way, tension is in the x direction. So that one's easy to account for. The normal force is in the y direction, so it's easy to account for. Two of the three forces are easy to account for. The only one that I'm going to have to worry about the components is this weight vector. So we do this very often when we have inclined planes. We rotate the coordinate system, and then you end up having to resolve the components of weight along the incline and perpendicular to the incline. So what I'm about to do, you'll do many times, and I encourage you to practice it and get this geometry down so that you're used to drawing this. We need to find the components of mg, perpendicular and parallel to the ramp. And here's how it goes. I'm going to draw this horizontal line here. This is the angle theta. And then I'm going to draw this vertical line here. Now you need to convince yourself that if this is the angle theta, so is this. There's a couple ways of doing that, but exercise your geometry and convince yourself that's the case. Now I'm going to draw one more reference line. This one straight along, following the normal force. If this is the angle theta, then this opposite angle is also theta. And this is the one that we really needed to get. We needed to get the angle theta inside where this weight vector is. And now we can draw the components. Let me draw them in green and orange. So here's a component of the weight that's perpendicular to the ramp. Here's a component of the weight parallel to the ramp. Now let's write how long each of these components are. This green one is adjacent to the angle theta. So with the hypotenuse right here, this is a right angle, of course, this green component is going to have a length of mg cosine of theta. This orange one is opposite the angle theta, so it'll have a length, I'll put it down here, mg sine of theta. So this thing I just did, resolving the components of weight parallel and perpendicular to the ramp, is not necessarily easy, but it happens so many times in mechanics that you want to practice this. You want to get good at this maneuvering that I just did, drawing these angles theta, finding the components of weight parallel and perpendicular to the ramp. Practice that enough times until you're good at it, and then you'll be in good shape for these ramp problems. Okay, so there's our free body diagram. Now we're going to add up the forces in the x and in the y directions. Let's go for the x direction first. My x direction is up the ramp. So I need to look for forces that are in that direction, aligned with the ramp. And I see two. I see this tension T that's aligned with the ramp. And then as I look around, I say no, no, but yes. This orange vector here is also aligned with the ramp. It's going not in the positive x, but in the negative x direction. So what we get when we add these forces up, we get tension going up the ramp, and we have mg sine theta going down the ramp. That's the sum of the forces in the x direction. Add up all the forces in the x direction. I find two. Tension going up the ramp, the orange component, mg sine theta, going down the ramp. And that will tell us mass times acceleration. The right-hand side of this we'll deal with next time. Now we do the same thing for forces in the y direction, perpendicular to the ramp. The y direction is this way, off the ramp. So now I look through my free body diagram for forces that are perpendicular to the ramp. And again, I see two. I see this normal force going in the positive y direction, and I see this green one going in the negative y direction. So I end up with n minus t cosine of theta equals ma y. All right, normal force in the positive y, the green one, mg cos theta, in the negative y. And I see that I miswrote that. I don't know why I put t cos theta. mg cos theta equals ma y. All right, it's good to look over your work and catch errors. So normal force in the positive y, mg cos theta in the negative y. So that's that one. One more. Let me erase this, and we'll look at our last situation. This one's going to have 3 boxes in it. So this is going to be a system composed of 3 boxes that we're going to pull along a frictionless surface. So here's our frictionless surface. There's going to be 3 boxes here. Here's the first one. We'll call this one box 1. And we're going to tie a string to it so that it goes back here and attaches to the second box that we'll call box 2. And then there's going to be a third box that's sitting here like this, squeezed under this string. And the whole thing I'm going to pull to the right by attaching a string to it. There's my hand. I'm going to pull that way. All right, so what's going to happen is I pull on this string. It makes this thing move, which moves this one. And then 2 is going to plow into 3 and move it along, hitting it from behind. All right, we need free body diagrams. I'm going to draw this time 4 free body diagrams. I'm going to draw a free body diagram for block 1, for block 2, for block 3, and then I'm going to draw one more for the whole thing as a system. So let's start drawing these. We're going to have free body diagram of block 1, of block 2, of block 3, and then of the whole system. And then we'll write out all of the sum of forces equals ma equations. Okay, let's look first at block 1. Our job here is to focus on this one, ignore the rest of the world, and draw every force that acts on that box. Here it is. It has weight. Because I have 3 things in here, I need to keep track of all of their masses. So I have m1, the mass of box 1, times g. There's a normal force on it, n1. And then I see 2 strings attached to it. There's this string pulling it to the right. I'm going to call that tension 1. And then there's another string that'll pull it to the left. I'm going to call that tension 2. Those tensions are probably different. All right, now, box 2. It has weight, m2 times g. And then if we look closely at this guy, we're going to find things that are touching it, pushing or pulling on it, and we're going to put all of those forces. The ground is pushing up on it, so we have n2. I see a string attached to this box, and that string is going to pull it this way. That is the same string that was pulling on this guy the other direction, and I called that one over here T2. So I'm going to have the same tension here, but this time pulling it to the right. So T2 is going to go this way. There's one other thing that could be touching, pushing or pulling on box 2. As this whole system moves off to the right, block 2 is going to plow into block 3 from behind. So as 2 exerts a force on 3, 3 is going to exert a force back on 2. And that's the one I'm interested in here, the force on box 2. So there's going to be a normal force here exerted by box 3 on box 2. All right. Now let's do free body diagram for box 3. It has mass, so it'll have weight, m3g. The floor is pushing up on it, normal force on 3, and there's only one other thing pushing on block 3. If I focus my attention on this box and ignore the rest of the world, forget this string, it's not touching block 3. That string's not touching block 3. The only other thing that's touching it is 2 plowing into it. That's going to exert a normal force. You could call it the normal force that 2 exerts on 3, but I'm going to call it N32 because I know from Newton's third law that N23 and N32 have the same magnitude in opposite direction. They're an action-reaction pair. 3 pushes on 2, 2 pushes on 3. So I'm going to call this the same thing I did on block 2's free body diagram. I'm going to call it N32. Magnitude and direction. All right, last one, the system free body diagram. The idea now is to draw a free body diagram, forgetting all of the pieces and parts that make up this, but to draw it as one thing. So consider everything inside this orange boundary to be a thing. And we're going to draw things that come in from outside and act on that one object, our system. What I see is that there is weight. So we have mass 1 plus mass 2 plus mass 3 times g, the whole mass times g, the mass of everything inside this orange boundary times g. And there are normal forces, N1 plus N2 plus N3. And there's one other thing coming in from outside, pushing or pulling on this system, and it's this string right here. It's tension T1. Now tension T2 doesn't show up here because it's inside. We're only drawing things that come in from outside and move this. This is what's called an internal force. And notice that it will cancel. This tension T2 is going to pull to the left on this piece and pull to the right on this piece. When we add them, they cancel. And the same thing happens down here. This internal force is going to cancel. The only thing that can affect the way a system moves as a whole are forces that come in from outside. The string comes from outside, so it's going to change how it moves. But this tension force is inside. It can't affect how the whole system moves. It could affect how it rearranges itself inside there, but it can't move the whole thing. We draw forces that come in from outside. Okay, all that remains is to write out the sum of force equations. I'll do that for a couple of these. There's nothing new here, so we probably don't need to do them all. Let's write out sum of forces along x and y for 2 of these free body diagrams. All right, let's do first block number 1, and then we'll do the whole system. So we'll do these 2. If we do first block number 1, it tells me to add up every force in the horizontal or x direction. Let that be x and let that be y, and we'll set it equal to max. Now what do we have? Well, on block 1, sideways, we have tension 1 in the positive direction, tension 2 in the negative. So we have T1 minus T2. And that will equal the mass of block 1 times its acceleration sideways. Notice that I have a 1 here also. I was adding forces from block 1's free body diagram, so I put block 1's mass over here. In the y direction, in the vertical, I'm going to have N1 minus M1g. That will equal M1ay. Okay, so there's that one. Let's do the sum of the forces for the system also. If we look at this system free body diagram, we're going to get a different thing. When we add the forces up, all we have is this tension. The only force coming in from outside, pulling sideways on this system, is that tension from the string on the right. So that tension will equal the mass of the whole system times the system's horizontal acceleration. Notice again, I was using the free body diagram for this system, so I'm going to use the mass for the system. In the vertical or the y direction, I see 3 forces going up, all those normal forces, and 3 weights going down. So I'm going to have N1 plus N2 plus N3 minus M1 plus M2 plus M3 G equals, I've run out of room, so I'll put it down here, M1 plus M2 plus M3 AY. All right, so that's how you do these free body diagrams. The idea is to give you a picture that lets you correctly add up all of the forces in a given direction. Next time, we'll start dealing with the right-hand side of this also and apply Newton's second law to some problems.